So like all of our problems in section 4.4, we should start by looking at the domain here. So let's consider that first, the domain. What problem might we run into in working with a function like number 20? Yeah. What's underneath the root has to be greater than or equal to 0. So, in other words, 9 minus x has to be greater than or equal to 0. Or 9 is greater than or equal to x. Flipping this around, equivalently, x is less than or equal to 9. It's probably easier to look at and interpret that way for some reason. So our domain is negative infinity to 9. Now, can I use 9? Okay. Since it's election day, we should vote on it, right? You know, math by democracy. Who thinks we should use 9? All right. Can you take the square? If we put in a 9, you'd get the square root of 0. Can you take the square root of 0? Yes. So we can use 9. All right. So let's put in a 9 there with brackets. That's our domain. Want to keep track of that. That's going to become more important when there are optimization problems later on. As far as the derivative is concerned, and eventually we're going to need to work our way to the second derivative, but let's start with the first derivative. All right, yeah, it's not a bad idea to rewrite that as x times 9 minus x to the 1/2 power. But what rule are we going to have to use to differentiate this? Chain rule and product rule, all right? Or our power rule. So yeah, basically I think the only wrong answer you could have given me would be the quotient rule. So you had a pretty good chance of getting that one right. We're going to use them all. But the first thing you see, of course, is a product. So it's going to be the derivative of the first times the second, and the derivative of the second times the first. So what's the derivative of the first going to be? 1. So 1 times 9 minus x to the 1/2 plus x times, well, it's going to be 1/2 9 minus x to what power? To the negative 1/2. That's the derivative of the outside. Somebody said chain rule, right? What's the derivative of the inside? Times negative 1. Let's clean this up a little bit. In fact, let's clean it up a lot. But are you okay with our first pass at the calculation of this derivative? All it is was the product rule and a little bit of the chain rule. If you look here, we've got 3 terms that we're going to bring together. X, a 1/2, and a negative 1. Those are all multiplying together. So I'll rewrite this as 9 minus x to the 1/2 minus x over 2 times 9 minus x to the negative 1/2. Now here's where that tricky factorization comes into play. We want to factor out the term with the lowest exponent. And these are going to be, typically they're going to be negative. So the smallest exponent, the furthest exponent to the left. So I'm going to factor out 9 minus x to the negative 1/2. 9 minus x to the negative 1/2. Now what that means is that each of these terms is going to get divided by that 9 minus x to the negative 1/2. So 9 minus x to the minus 1/2. All right, yeah, the second of these terms has some nice simplification in store for us, right? This whole thing disappears. All you're left with is minus x over 2. Now, what's going to happen with these two terms? Well, one thing you should notice is that they have the same base. So you need to subtract exponents. Let's do that carefully, but I'm not going to write it down. 1/2 minus negative 1/2. 1. So I'm going to get something to the first power. So 9 minus x to the minus 1/2. 9 minus x to the first power minus x over 2. Okay, that's the tough part. A little bit more work left to do. Minus 1 and minus 1/2 are your coefficients of x. These are your like terms. So I'm going to combine those. I'll make that 9 minus 3/2 x over 9 minus x to the 1/2. When it comes down into the denominator, it becomes positive. The exponent does. Okay, I did two things. I brought this down into the denominator and made the exponent positive. Now, the other thing that I did here is I looked at these and said, you know what, those are like terms. Let me rewrite that a different way. Let's think of it as 9 minus 1x minus 1/2 x. So all I did is I combined like terms. Negative 1 plus negative 1/2 is negative 3/2. And that's where I got that. This term stayed in the numerator because it has, essentially a positive exponent of 1. This one came down into the denominator because it had the negative exponent. All right, does that help out with the derivative there? That's the trick that I warned you about in problem 17, is to know how to do this kind of factorization. I really don't know how you would do these problems without this kind of a trick. You're going to struggle. I mean, might be a way to do it, but this is my best recommendation to you. Let's keep going then. Let's figure out right here where the derivative can change signs. Now, what does the derivative tell me about a function? Kind of going back a little bit. What's the derivative tell me about a function? All right, what's positive or negative tell me about the function then? Increasing or decreasing. So we're not looking at concavity yet. We're looking at increasing or decreasing here when we're looking at the sign of the derivative. Let's see where the derivative is 0 or doesn't exist. In other words, where can it change signs based on where the numerator equals 0 or where the denominator equals 0. So let's figure out where the numerator equals 0. That would be 9 minus 3/2 x equals 0. For convenience, let me move the 3/2 to the right side. So the 3/2 x, that becomes positive. If you multiply both sides by the reciprocal, 2/3, 2/3 of 9 gives you 6. So that's where the numerator equals 0. Let's figure out where the denominator equals 0. It's going to be 9 minus x to the 1/2 equals 0. If you wanted to or needed to solve this kind of a brute force way, you could square both sides and get 9 minus x equals 0 squared. But that's just really x equals 9. You can kind of see that here. All right, so those are your critical points. Now, one of them is at the edge of the domain. So the function is really not going to change signs there. But it is a critical point. In fact, you're going to get a vertical tangent there. The big thing I wanted you to see was how we factored this and how we cleaned it up. So before I work with the second derivative, how are we doing with the first derivative? This is the part that I want you to know. All good? Thumbs up? Okay. All right. Cool. All right. Let's keep going. I think I mentioned a little bit ago that I'm not going to take the time to go all the way through calculating the second derivative with you. It's a lot less joyous than the first one. So here you go. F double prime of x is going to be negative 9 plus 3/4 x divided by 9 minus x to the 3/2. So there's your second derivative. As with the first derivative, I want to know where this can change signs, where it can go from positive to negative or negative to positive. Those are the points that I'm interested in. Okay, so where does the numerator equal 0? And where does the denominator equal 0? So let's take a look at the numerator first. Numerator equals 0. Negative 9 plus 3/4 x equals 0. This time I can get rid of the negative in front of the 9 by moving it to the right hand side. I get 3/4 x equals 9. The quick way to solve here is to multiply both sides by the reciprocal of that coefficient. What would that be? What would that mean here? Multiply both sides by 4/3. Say again? Yeah, we get x equal 12. No one's complaining about that. Yeah, you're all just trying to keep up. All right, I understand that. But there should be some complaints about this. What's wrong with 12? Ah, well done. It's outside of the domain. Just the function just doesn't exist there. So even though the second derivative could change signs there, the function itself doesn't exist at 12. You'd get an imaginary number. So it can't change signs there. 9 is at the edge of the domain. When we look at the denominator equals 0, that's going to be 9 minus x to the 3/2 equals 0. That's going to be the same as before. 9 is equal to x. So, well, no, not necessarily. It just means that that's a sticky point. All right. But basically what this is saying is that the function has a second derivative that's always either positive or negative. It doesn't change sign. So it's either always concave down or always concave up. We don't know which. So let's make ourselves a quick little table. X, F, F double prime, any. Doesn't matter what we test as long as it's a point in the domain. All right? Well, what point do you want to test? Yeah, I'd test at 0. Yeah, 0 looks pretty easy. So if I test a 0 in f double prime of 0 is going to give me negative 9 divided by 9 to the 3/2. Do I need to calculate the value for 9 to the 3/2 in order to find out what this is telling me? It's negative. Perfect. That's all we needed. It's negative. And if it's negative, then you're going to have a concave down shape for the function. It should be concave down throughout its interval. Let's confirm that. Now, one thing that I strongly encourage you to do is make sure that the conclusions you get on paper match what you see from their graphs. So in this case, it's pretty easy. You can take out your graphing calculator. I'm going to do it here on Desmos. So we want y equals x times the square root of 9 minus x. And if we can get a graph here, that would be wonderful.
That function looks so innocent.
There you go. So concave down throughout the interval, throughout its domain, really. So from 9 here all the way through to negative infinity. It's concave down in its shape. Nice. Worked out pretty good. Any thoughts on problem number 20 here? Well, the function where it changes signs, or where it's equal to 0, is where it can change signs. So where it's equal to 0 in the denominator, or where it's equal to 0 in the numerator, all that's places where the function's derivative or second derivative, as the case may be, can change signs. It can go from, say, positive to negative, or negative to positive, etc. And it's in between those points that we're testing the signs. So you got to find these points first. And in our case, we got a point at, what was it, 6 and 9. Since 9 was at the edge of our domain, we didn't really have to test it. There's nothing on the other side of 9. I mean, you could test a point out there, but you wouldn't get anything. It's not part of the function. So we didn't need that one so much as we needed the point at 6. 6, we tested things on either side. Or you could test things on either side. Anything else on problem 20 here? Did I answer that for you, or do you need a little? Okay. Let's do a couple more. Do you want to do problem number 22? It's going to give us a little bit more practice with that kind of factorization that was a key point in problem number 20. All right, let's do that one then. F of x is x plus 3 over the square root of x. Now, this one, as well as the test, have a little trick that can make our life in terms of finding the derivative a lot easier. Before I go and do the derivative, let me take care of one thing first. What would that be? Good, the domain, thank you. What's our domain here? Good. X is greater than 0, so 0 to infinity. It can't be 0 itself because that would put a 0 in the denominator. So you have to have a parenthesis around the 0. Now, as far as playing with this is concerned, I guess the first thing is to think of the denominator as x to the 1/2. And the next thing I'm going to do is I'm going to divide both the numerator and denominator by both terms in the numerator by the term in the denominator, x to the 1/2. For the first of these terms, I have two things with like bases, so I can subtract their exponents. And I'll get x to the 1/2. And for the second one, I'll write that as 3x to the negative 1/2. Now I need to plow through and find the second derivative for this thing. So I'm thinking it's easier to find the second derivative here than it would be to find it the way the function is written originally. What rule would I have to use to differentiate this as it stands originally? Quotient rule. In fact, remember you got to use that twice, so wow, wouldn't that be a lot of fun? Save that for your Saturday night. Let's differentiate it from here. F prime of x is going to be 1/2 x to the negative 1/2 minus 3/2 x to what power? What power am I going to get for that one? 3/2 x to the, thank you, negative 3/2. So negative 3/2. let's differentiate it again. We need to find the second derivative. So let's do that. F double prime of x is going to be negative 1/4 x to the negative 3/2. Any takers on the rest? What am I going to get on the rest? Plus 9/4, good, because 3/2 times 3/2. X to the negative 5/2. Nice. I don't know, what do you think? Should we have used the quotient rule? No. Yeah, you'd still be working on that. Probably for a few more minutes, too. So, no, I want you to do it as easy as possible. In fact, on the test that you just got back, one of the things I gave you was f of x equal cosine x over sine x. And I asked you for the derivative. The easiest thing possible is to notice that, oh, that's the cotangent of x. And the derivative of the cotangent, anyone? Minus cosecant squared of x. That's what I wanted. All right. So, and just FYI, we did that one in class when we did the quotient rule. So, okay. So yeah, I want you to do it as easy as possible. Now, we come down to the part that we did in the last section. That is, we have to factor out something. Which term do you think I'm going to factor out? All right, so 1/4 x to the power, you want to go for the smaller one, the one that's farther to the left on the x-axis, so to the negative 5/2. Now, if you can do this in your head, great, power to you. I'm showing this step because I want everyone to see what I'm doing, and I don't want them to get lost. But if you can do it in your head, that's great. You don't have to show me all the work here. So negative 1/4 x to the negative 3/2 divided by negative 1/4 x to the negative 5/2 plus 9/4 x to the negative 5/2 over negative 1/4 x to the negative 3/2 or negative 5/2. So you should get, at the very least, some nice simplification from part of each of these terms. In the case of the first term, the negative 1/4 disappear. In the case of the second term, the x to the negative 5/2 disappear. To find these a little bit more simplification we're going to get. All right. So negative 3/2 minus negative 5/2. Go ahead, Mace. 1. Yep. So I'll get x. A plus and a minus here. The sign between those middle terms is a minus 9. The 1/4 cancel each other out because they're both in the denominator. So like that. Now the 4 is in the denominator. This negative exponent can go down into the denominator as well. So you get x minus 9 over, and let's see, there's a negative sign, I'll leave that out front, over 4x to the 5/2. Wow. So a lot of work, a little bit of finesse at that last juncture to get this thing factored into a nice workable form. You'd eventually get there with the the quotient rule if you used it twice. I'm just thinking that it might take a while, so it wouldn't be a whole lot of fun. The question now is, where can this change signs? So where can this change signs? All right, so let's set the numerator equal to 0. So the numerator equals 0 is going to be at minus of x minus 9 equals 0. And the denominator equals 0 is going to be 4x to the 5 halves equals 0. And I'm going to get two solutions here. X equals 9 and x equals 0. What can you tell me about one of these solutions? Yeah, it's not even, 0 is not even in the domain. So the function's not going to change its concavity there. It's not going to change signs because it's not even part of the domain. So the only place where the function can change the sign in the second derivative is x equals 9. So f of x, f of x, and f double prime of x, and 9. Don't worry, they're guaranteed. So's the pen. All right. Now just test points. Thank you. It's up to you. What function am I going to put in my calculator if I don't trust myself to do it by hand? What function am I going to put in my calculator? Second derivative. All right. You're going to put this function in your calculator. To the left of 9, you're going to see that the second derivative is positive. To the right of 9, you're going to see it's negative. So in terms of our shape here, that tells me that it's concave up and concave down. So concave up on the interval 0 to 9, concave down on the interval 9 to infinity. Yay! Sure. Is there someplace in particular?
It was where you got 1. When I was minusing the exponents, I got 2.
Okay. Well, it's 2 over 2, right? Because when you subtract these exponents, it's negative 3 halves minus negative 5 halves, which is negative 3 halves plus 5 halves, which is 2 halves, which is 1. So that's what's happening with the exponent. Okay, you're welcome. 0 would create a 0 in the denominator, and you'd end up dividing by 0. So that's why we left off 0. You can take the square root of 0, but unfortunately this term is in the denominator. So once you take the square root of 0, you still have a 0 in the denominator, and that's undefined. You can't divide by 0. Yeah, please. Okay. No, you should have got a positive number here. Did you include the negative that's out in front here when you put that into your calculator? Okay, that will make a difference then. Anything else? I think I saw. No. Okay. You can put the original function in if you want to graph it. In fact, graphing it's a good idea. Let's take a look at that. The original function looks like this. But the original function, you're just going to look at that when you're ready to graph it and see what it looks like and make sure that it matches your results. So, it should match your results, but this is a great example of why you need the calculus to tell you, where it's happening. I mean, can anyone look at this and go, oh, I see it. It's right here that it goes from concave up to concave down. Yeah, you do, but you're an educated man. No, the rest of us are too, but no, you just can't really see it. I mean, to me, it looks like a straight line. It doesn't look like there's any concavity at all. The table's really not going to show you much. We will use the table in section 4.5, but right here it doesn't help us out too much because even with a good graph, And this is a pretty good graph. Boy, there's nothing that looks magic about this point. It doesn't look striking to me. Does it to anyone that all of a sudden it changes from concave up to concave down? At least we can see to the left of this, yeah, okay, that looks like it has a concave up shape. And at some point it becomes concave down. If they wanted to tell me 9, or if they wanted to tell me 20, okay, whatever. Yeah. Let's see, what do we do with number 20? Let me back up a second here. Number 20. Yeah, we were just seeing that it had a concave down shape forever, is what that showed us. This one, you can kind of see the concave up shape. The concave down shape just isn't there, in my opinion. I mean, it is technically, because we calculated the second derivative. But visually, I don't see it. All right. Thanks, Justin.
Are you going to make us graph, the actual graph, based on the data that we collect? Like,
That's the whole point of section 4.6. Yes, coming up. So let's finish off this section with one last example, and that is how to use the second derivative test. So it's problem number 38. So let's go back and think about our functions. And I'm going to go back to the beginning here. Suppose you had something which was a critical point. And you don't know if it's a minimum or maximum. But you do have the second derivative. If I calculated the value of the second derivative at this point, and this is a maximum point, right? What's the value of the second derivative going to be? Negative or positive? Negative, right? Because it's concave down. So near a maximum, the second derivative is going to be negative. So one way to test whether or not your point is a maximum, not a minimum, is to look at the value of the second derivative. It's called the second derivative test. And likewise, if the value of the second derivative at a critical point is greater than 0, then you have a minimum, because that reflects a function which is concave up. And that critical point then is going to be a minimum. So let's apply the second derivative test to problem 38. F of x is negative x cubed plus 7x squared minus 15x. Where do you suppose I should start here? Bonus points. Excellent. Domain. Yeah. The domain is everything. This is just another polynomial function. Domain is negative infinity to infinity. Let's work on some derivatives. F prime of x is negative 3x squared plus 14x, thank you, minus 15. Now in using the second derivative test, you're going to apply the second derivative test to the critical points. So I actually need to find where this is actually equal to 0. And I can do that by factoring. That's negative 3x plus, is it plus 5? Yeah, plus 5 times be x minus 3. That's going to be equal 0 when one of these two things is 0. So when either x minus 3 equals 0, in other words, x equals 3, or negative 3x plus 5 equals 0, which gives us x equals 5/3. So these are our critical points. We don't know if they're minimums or maximums, but something's interesting happening there. We just don't know what. To decide, we'll apply the second derivative test. So let's calculate the second derivative here first. Thank you, ladies. Negative 6x plus 14. And let's find the value of the second derivative at both of these. So f double prime of 5/3 and f double prime of 3. So negative 6 times 5/3 plus 14, positive 4. And for our other one, negative 6 times 3 plus 14 is negative 4. The important thing to get out of this is that because this is greater than 0, it's greater than 0, that means it has a concave what shape? Up. It has a concave up shape. Now, if something's concave up, is your critical point going to be a minimum or a maximum? Minimum. So this little triangle of dots here means therefore x equals 5/3 is a minimum. All right, because the second derivative is greater than 0, the shape of the function at that critical point is concave up. If you have a critical point where the function is concave up, it has to be a minimum. If you have a critical point where the function is concave down, then what has to happen? Yeah, this is a max.
So it's opposite of what you would think.
Maybe a little bit, yeah. Yeah. Now that's the second derivative test. You don't always have to use the second derivative test. We can use the first derivative test. It depends what you have, and it depends on the situation. The first derivative test is stuff that we've already used. So let me lay out our function and its derivative and a couple points here. The points are 5/3 and 3. So we know the second derivative or the first derivative is 0 at these points. You plug the first derivative into your calculator or one way or another test points here, and let's see what kind of a shape you're going to get. You're going to get negative, positive, negative. So what's happening with the function? Well, it's decreasing, increasing, and decreasing. So if the derivative is decreasing and then increasing, what kind of a point, or excuse me, the function is decreasing and then increasing, what kind of a point does 5/3 have to be? Minimum. So minimum at x equals 5/3, and then a maximum at x equals 3. So that's the first derivative test. Somebody asked me in my morning class, are you going to tell us what to do? Probably not. I generally don't like to tell you what to do. I would encourage you to know both, because depending on the work that you've done for a particular problem, one may be more convenient than the other. The second derivative test gets very convenient in our optimization problems in section 4.8. That's where it's really handy. So I'd keep that one around, but whatever works. Sometimes you will be asked to prove that something's a minimum or a maximum, and you've got both. Okay, let's take a break here. For homework, try problems 1 through 47. Section 4.4.